Okay, so you know the software already. The first thing we have to do is in the morning, of course, we have to calibrate the instrument. And therefore, you go to Instrument menu and say Calibrate. You place the white tile on the instrument, like we have said, best possibly with the label showing up. And then you just click OK, and you hear like the instrument is measuring. Then you place the black trap. Maybe you put the USB label. The mirror should face down. Actually, no, like this. The mirror, let's say the mirror should be up but facing down. Okay? Yeah, we can mark it later on. Okay, and once you did this, the calibration turns green on the instrument. And the next thing you have to say here is calibration succeeded. Okay. Then the first thing we do right now is that you have it on the video is the configure menu for the instrument. The instrument can measure two different modes, specular included and excluded, or it can measure both in simultaneously one measurement, specular included and excluded. The meaning of that is following. This instrument is using a so-called sphere geometry. So that sphere, yeah. So that means if I open it up here, you see there is a white sphere. This is a ball which has a white coating, and the ball is illuminated from when the measurement takes place. It's illuminated from the bottom. So that means there is white light going into this ball, which is completely scattering. So you have a diffuse illumination. That means you have light out of every direction on top of your sample. And this makes this instrument able to measure two different modes. And you have to decide which mode you want to use. The one is, this is a plastic sample. And this is, of course, one material, but we define this to be two colors. This is a glossy color, and the other one is a matte color, of course. So we see a glossy color always appears darker, and the matte color always appears lighter because of the matte surface. Okay? With that instrument, I can select to measure both areas as one color. So I can measure independently from its surface, or I can select to measure both areas as different colors like I see it here. And we will do a test measurement to show you what the meaning is. Okay? So, to measure both colors as one color, to measure the pigmentation only, you would set the mode to specular component included. This is what you did already, and this is the default mode too. But as in Color Master, you can at any time you can switch between included and excluded. We can also set it to the simultaneous measurement of both conditions, because both conditions are anyhow measured in one process. The lens position to be set on auto is the recommendation, because then the instrument is realizing itself when you change the aperture plate. It's adjusting completely automatically, and this is a recommendation. If you, of course, change the lens, you have to calibrate new. Each lens or each aperture size has to be calibrated, but once it is calibrated, it is valid for a day, and then you can switch between the plates. Okay? And what you have to do once a month is the so-called, what you can adjust here is the UV condition of the lens. As you know, the sun has a lot of UV light, of course, and UV light is not visible for our eye, but it has a certain impact when you use optical brightness. So in this light box, of course, you might have a UV lamp, and if you switch it on and we place our shirts into it, they start illuminating bluish. This is optical brightness. What's happening there is that the UV lamp itself is not visible for our eyes, but the optical brightener is a chemical agent which puts the energy from the UV and puts it into the visible area at the blue. Therefore, we start glowing blue. Okay? And now you can decide whether you want to measure with the UV content of the lamp source, because this lamp source is like the sun, it has a UV content, or if you want to exclude it, because there is a filter glass which we can move in front of the lamp, and then you would exclude the UV content.
Which one is recommended?
The recommendation is now set, which is the D65 recommendation. This is the standard position which is simulating daylight. The daylight position. And I will keep it like this.
So for interior colors, we have to exclude.
Interior colors, you could exclude it, yeah, to be more closer, but it makes not a big difference. No. Because I guess you will not use optical brightener in your paint. The only thing you might have is that you have contrast cards, or cards when you make drawdowns, which are optical brightener, and this is a little bit dangerous. This is the only danger with it. That the card is optical brightener, because then the UV lamp could be an influence on the measurement if the opaque layer is not fully hiding, not fully opaque. But I believe you're... this is not fully opaque, you see? So you see the black through it, through the paint layer. And
in this case, we can go contrast ratio.
Yes,
like transparent.
Yes, of course. Exactly. You can make contrast ratio measurement, but in case that these cards have a UV content, you will measure a different color than the real color you want to match, or that you want to measure. So, to show you this, we can quickly stop the recording here, maybe, or pause the recording. Now pause it. Here we are back with the recording. So my recommendation is to set it to UV excluded then, because now you hear the instrument moving, and it's moving the UV filter in front of the lamp, so that we don't have...
It doesn't matter about this included, excluded.
It does not. It's a different story than included, excluded for the gloss component. The one is the lamp, which you can, where you can include or exclude the filter. And the other one is the gloss component, which makes you integrating the gloss, which means you measure these two samples as one color, or excluding the gloss, which means the sample will lose light on the gloss. Because of gloss, it looks darker then. This sample would lose less light because of scatter. It looks lighter again. We will have a look on this right now. First of all, as we have changed the UV component, we have to calibrate again. So whenever you change a condition, you have to calibrate. Therefore, we go again to Instrument. Calibrate. It asks for the white tile again. Black trap. Yeah. That's it. Calibration succeed. And now we make a measurement of a standard by just using the standard wizard. You have explored this already, and we measure the backside of this paper as it has very high optical brightener content. Or we measure the white tile as a standard first. So I take a measurement, I just click to next, I don't take an average, I click simply the measure button, I go to next, and I call this measurement white tile. And then I save it into the X-Rite Incorporated customer, or into the test customer, let's say. Save and exit. And now I have the white tile as a standard. To show you the impact of the optical brightener, I will turn on a certain view, which is the spectral curve view for spin first. I get rid of trend and the formula. So you see, a white tile is more or less giving back 100% of reflectance. Okay, so this would be an ideal white which would give exactly 100% of the light going to the sample as a feedback back. There is no such ideal white existing in the true world. Therefore, our white tile gives approximately 73 to 85% back. Okay, this is also the values on the certificate for your instrument. So, now to show you the impact of optical brightener on such a paper, we simply measure the backside of this paper here as a trial with this button here, with the measure trial button, against this white tile standard to see the difference. So by default, this measurement command for the trial is starting up minimized, because the autosave option is on, and we can turn the autosave option off, and the lot ID would be the name for the trial. If we don't give any name, every trial gets a number and the date and timestamp. So every trial is by default defined with the date and the timestamp. Okay, in this case I simply call it optical brightened paper. Oops, we forgot about the A. No A? Am I on the Arabic keyboard or something?
Zooming in the project screen. Try to have
okay. 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 Yeah, there are commands. So, no UV is important. This is now a measurement of the optical paper without UV content, as we have excluded the UV content. And I measure this. Then I save it. And I close it. And you see actually, this is also as well a white curve. It's a little more bluish because here is the blue area. It's a different white than our white tiled white, but at least it looks white. And now we go again to instrument menu, configure, to set the UV content to P65 again, so to include UV light, to have the impact like we have it in the light box. You say OK. The calibration now is still valid because we did configure this, we did calibrate this condition already before. So we measure again the white paper, now with UV light, and you will see a massive difference now. If I go to measure trial, and I say this is optical brightener with UV, did I save it?
No.
I did not save it. Once again. Optical brightener with UV. Measure. Save. Now it finds already a standard in your database which would be even closer to that. But we say we stay with the current standard because we want to compare it against the current standard, and it gets a massive fail. Because this is exactly now the effect of the optical brightener. If I switch scatter, it shows all trials, and this is the same white color with UV excluded, which is looking white like the white tile. And this is even giving 130% almost reflectance, which is unlogical, because if I get 100% light to my sample, I would not expect more than 100% coming back from that sample, right?
It will affect even if it is opaque also?
Even if, yeah, this is now the big question we have to check. This is dry, right? This we can measure. So we will now take a measurement on your color, once with the UV lamp and once without the UV lamp. And if there is a difference, we will always exclude, because otherwise we would measure always the impact of the paper, which we of course do not want to measure. Okay?
Yeah.
So
But this is not
that
Yeah,
therefore,
this is
therefore,
also will not give that much effect.
the-
Even
the-
excluded
the-
as well as
I believe this is not a big deal because this is opaque.
okay.
Yeah, but on such colors like this, we have to be sure, and therefore, my recommendation is anyhow
Better
set it
than
to
to
UV
exclude
excluded,
it.
and that's it.
excluding the UV is nothing include and exclude the other option. Just only the UV light and then you will not be having any reading of your substrate.
Yeah, that's the point. We do not want to read the substrate because it's not.
Suppose some pigment in red with violet red, pigment violet red.
Yeah,
These and all will show some effect on your sunlight.
yeah, of course.
So if we exclude that UV light,
Then you might not see this effect, of
Yeah.
course. So then you have to include it again, but then you have to use cards without optical brightness because then you have a total mix
so
of.
that
You do not measure what you want to measure, of course.
in any case we have to go for our logic.
Once again,
If it is depending upon the
yeah,
substrate and depending upon the sample.
yeah.
We can just work with it excluding. For example, purchasing new concentration card having the no brightness.
Yeah, the
And
problem.
you can find it in an ether card
Yeah,
or another source of card, but you need to solve the give us the sample and you chip it to the right box.
yeah. You can even go to your local print shop here and ask them to produce such cards for you. You don't necessarily have to need Laneta cards, but
Yeah,
you
we can
have.
call them and we can show them.
You have to be sure that they print this on a paper which is not optically brightened. And to be sure about this, you should get samples and then you test it with this UV lamp. And as soon as they are starting to glow bluish, you can forget about it.
You know what we told them?
It's common because the paper industry wants to have a paper looking the most white possible, of course. They want to have paper looking white,
Yes.
of course. But in your case, for color measurement, you can really forget about this paper. It's better to have a slightly yellow shade or yellowish shade on the paper instead of having optical brightening. I have even seen cards, I'm not sure in Egypt or even here,
there is
which are yellowish.
Sheen card and Sigma card.
Yeah, they are
They are
okay.
little yellowish.
Yeah,
Little
yeah,
yellowish.
which is
the
okay.
chips, yeah.
Yeah, which is okay because
Yeah.
if you turn the UV lamp on, those cards will not
Yeah.
change.
It is little yellowish.
And as long as you make visual assessment, it makes no difference or not a big difference. But for the measurement, it's a real because you see this is a delta E of 50
Between white and
between white optical brightness and the same color unoptical brightness. Or let's say no, sorry, that's not 100%.
Between the cards, it is-
Between the white tile and between the cards, it's even higher. So now I did this button is to make any trial to be a temporary standard, and now I did make the optical brightness trial to a temporary standard, and you see against itself it's 0, but if we compare it against sample number 1 which was without UV, it's even 12. So on one paper, on this side, only the impact of light gives a delta E of 12. Okay, so this is really dangerous.
So we have to exclude
Yeah.
at the moment.
Yes. If you want to work with UV, you need to bring card not including optical brightness. And if you mention to any printer company that will produce for you, mention to them, I want to have optical brightness. You immediately know it because they want to make their own cards having optical brightness.
This is from our local.
Yes, I know. This is common in the industry. But once you mention to them, ask them that I need it without optical brightness. Normally they print it because you give them the sample. I didn't care about because they think that the customer he doesn't want the optical brightness.
But are we on recording still?
Yes, we are recording.
Oh.
You want to pause?
Yeah, of course.
But you're the
Yeah, now it's green again. So we did calibrate the instrument for certain conditions now. Where's the mic? Somebody's hearing me. Here we go. And we did calibrate the instrument for certain conditions. and I would really recommend to put it to UV excluded. You should also not use the model transform. The 8400 was another benchtop device of the former X-Rite. X-Rite and Greatag Macbeth merged their companies, and the 8400 was an X-Rite model. And for existing customers using this 8400, there is a model transform mode in this driver, which makes this instrument measure more close like the 8400. So of course you don't want to use it, you want to use this instrument as it is. So please always check that there is this enable model transform is unchecked. I would now recommend the excluded mode, the auto mode, and spin and specs we still have to discuss about. By default, I would say you will always measure specular included, the standard mode, because you want to know if the color is okay. Okay? I set it right now to specular component included, excluded. Click OK. Yeah. Yeah, so this is two things. The UV component can be adjusted to two individual positions. It can be to the defined D65 position, or it can be excluded. This is the UV adjustment. And the specular can be included and excluded as well, but what the specular really is, we will talk about now by doing some measurements. Okay? So I would like to make a standard measured on here, on the glossy sample. Again, you have seen this already. I go to standard, or just the standard wizard, which is this target disk button, or instrument measure standard. I want to take a measurement with the instrument, so I go next. And now I measure a sample on the red glossy, which is this one, and this I simply call red glossy. And I save this into the test customer as well. And then we measure a trial against this standard on the matte part of this sample, so on the different side of this sample, which is the matte side. You see? It is measured already. I simply give it a name, red matte. By the way, this lot ID can only use uppercase letters and numbers. I say save, and now you see the specular component included modus. This is the visual color, what the display on screen only. And this is exactly what I told you before. We have one mode on this instrument which can treat these two colors as one. That means this mode is only measuring the material independent from the surface. And we have another mode which can measure the color like we see it with our eyes. This is the surface unindependent or sensitive mode. Okay? So the mode which measures the pure pigmentation, the pure color only, is the specular component included mode, or spin like we call it. And the other mode is the specs mode, and there you see the glossy sample, which I did measure as a standard red glossy, is looking of course much darker than the matte sample. And this is according to what we see here. So in fact, if we watch the values for that, if we for example go for the view window, view and say LAB data, you see in spin mode it's almost zero. Of course we have some variances because I have scratches on the sample or whatever. But in specs mode, if I switch to specs, and I can easily do so because we have measured both conditions simultaneously, you see immediately that I have a delta E of 8 almost, and which is mainly coming out of the lightness difference. between the glossy and the matte sample. Okay? So we can keep it running like this, the software, or we can.
How much?
Pardon?
The included 0.68.
The included was here. Included is 0.68, which is only standard measurement variance, especially coming here in the B value, so in the yellowish content, because we did only one measurement, and it's a theoretical assumption. The visual color shows it the best, that there is almost no difference here. Okay? So you can.
Which D is recommended?
Pardon?
Which D is recommended? So there are many D.
Which delta E? Okay. This is the next we can talk about. My standard recommendation would always be delta E CMC or delta E 2000. The DE star is the standard delta E, which is really, as we are talking about the color space. Are you aware about this somehow? Basics of color? You have heard about it? Yeah? Okay. What we measure here is, if we measure color, we talk about 3 dimensions. We have the lightness, which is L, which is more or less the Z-axis, and then we have A and B. So we have a 3-dimensional space where we define color. The lightness goes from black to white, and the A goes from red to green, and the B goes from blue to yellow. So with this 3-dimensional system in place, we can define almost any color, because all red shades will be on this side, all green shades will be on this side, all yellow shades will be on this side, and all blue shades will be on this side. So we have the rainbow colors circulating around this, and we have, according to this, additional lightnesses. To show you this effect, I zoom out here to the 0 point of the system. You see, here is A and B 0. So by measuring such a red color, we are definitely in the red area, and this is actually a warm red, or a yellowish red, so we are in the yellow area as well. If it would become more into violet direction, then we would maybe have our color down here. So what you see here is the black cross is always the place of the standard. So in this case, L 48.676, A 44, B 24. So that means the A value is from here to here is 44, and the B value from here to here is 26, and this is exactly where our standard is. And the trial we have measured is slightly apart from this standard, which is indicated by this dot. Okay? So if we zoom in again, this is the detailed picture, of course, and therefore we have this line, because this line is always pointing to the 0 point. So if this line is moving into the left direction, we know that we have a red color. If this line would move into this direction, we would know that we would have somehow a greenish color. If the line would move up, we would measure a bluish color. So if I go into database and simply select, for example, this bluish color, guess what? The line is coming there's a this is specs, and we have no specs measurement here. I go to LAB spin. You see, we have a bluish color, so the line is coming from the top. Because if I zoom out again to the 0 point, here we go, I see exactly, I'm in the blue area right now. And if I zoom in again, in this case, you have already given a tolerance to this standard, which is delta L AB 1, 1, and 1. So you have given a cubical tolerance, which is a 3-dimensional cube. And if the color would be in between this cube, you would not have a problem. That's what it meant to say. And the interesting thing now is, this is the standard delta L, delta A, and delta B values. So that means you allow 1 unit in each direction, which is a rather huge tolerance space already, and which will not always be safe to have no problem with the visual. So my recommendation usually is the delta ECMC. And delta ECMC is giving a different tolerance space, which I will show you right now. To show you this, I have to change this tolerance set of this standard. And this can be easily done by clicking database, edit standard. So I want to change this certain standard by clicking edit. And then I go to tolerances and I add another tolerance, which would be then the delta ECMC tolerance for spin and D65 illumination. And I put this above the other tolerance to have it to be the priority tolerance. I don't want to save this as a standard, and then I say close, and you see now we have a tolerance space which is an ellipsoid. You see it here? And this is again the true world. Have you got a poster with you?
So the thing is that why we gone to that really is
Yeah, let him. Presentation. Stop. Basics of So this is quickly again. We sort the colors in from red to green and from blue to yellow. You see, and all the different colors are around here. Okay, and then we have something which defines a light color from a dark color, which is the lightness. So from black to white, this value goes from 0 to 100, and then we have something which defines a weak color from a bright color, or let's say a desaturated neutral color, which is a gray, from a bright color. So your shirt, for example, is not a very bright color, but an orange compared to this orange of your shirt would be a very bright color. So this is what we call chroma. This looks like this, from neutral to very colorful, let's say. And this is giving the 3 dimensions of color we have. So what I wanted to show you was how can I get back to this view to get all slides here? Here. Okay. Here we go. So this is the LAB model we discussed about. You see, this is the 3 dimensions we have, and in our software we usually display the A and B plot and the lightness on the side. Okay. This is the formulas for it. I believe we can leave this presentation to you as well. And this is what it looks like in the real world. We have the L-axis from black to white. We have the A-axis from -A greenish to +A reddish, and from -B bluish to +B yellowish. And if we go out there from the middle, the farther away we are, the more bright our color is. So if we compare this back to the red we did measure, and I just go into the test and into our red. You see we have an A value of 44 and a B value of 24. So if I compare this to this graph in the presentation, we could be, if we say this is maybe 60, we are somewhere here, already far away from the neutral, because this is a bright color. Okay? If we move in lightness, we go up here. If we get darker colors, we go down here. That's what it is all about. So the problem now is, unfortunately, this color space here is not visually linear. That means it is like this. This is a test Mr. McAdams did sometimes, and he found out that we have different sensitivity in our eyes for different colors. So if we have a bright yellow shade or an orange shade like this one here on the left side, a delta E of 1 would not be visible for our eyes. But if we have two gray colors with a delta E of 1, it's a really big distance. So that means taking the rule to always have a delta E of 1 is very dangerous, because in many cases it could not be a problem, and in other cases it could be a problem, of course. And therefore, the color science industry did create alternative delta E calculations to fix this problem. And CMC is such a calculation. CMC is the color measurement committee of the Society of Textiles and Dyers of England. So you see, if you give such a cubical tolerance like we had on this RAL shade, you might have colors, or you give a spherical tolerance with a delta E, you might have different approximations, but the problem is your sensitivity is less in chroma direction, that means into the direction of the bright color. So if you give a rectangular tolerance space, you have areas where you would have a path which are definitely failing. And therefore, such an elliptical tolerance space turned out to be the best match to our human eye, to our vision. And this is what the delta E CMC is calculating for. So what you would have here with such an LAB plus minus tolerance space, you would have really good numbers, so you would have get path results, but bad color on the paper. And therefore, the delta E CMC is the better approach to make this happen. Let me just see if there is a slide to show it, what it looks like. Yeah. So you see, the delta E CMC formula is taking care that for grayish colors, the tolerances are more tight. And for yellow or very bright colors, the tolerances are more open. And by having this in place, it is the best assumption, and then you can make a rule. Then you can say for yourself, our company will never produce a color being higher than delta E CMC of 1, let's say, or 1.5. Okay? This will be, by the way, the recommendation. If you do a 1 or a 1.5 and you fix that any standard you have to match with your paint is below 1 delta E CMC, you are fine in both cases.
Delta E CMC, sometimes if it is below 1, some delta E star, it goes up.
Yes, that's the point, because the delta E star is, that's exactly what's happened.
And
because
visually also we are feeling the difference.
Yeah?
By
Delta E CMC. When it goes 1, below 1,
yeah.
when we feel the difference of color.
Then you have to set your tolerance tighter. So there is one general rule
So
I will tell you. You should use the delta E CMC if the chroma value is higher than 10.
Initially it was like this one. Initially it was like this one. Delta E CMC. And this graph was also like this.
Yeah.
But when we started measuring some shades, it started saying fast.
Yeah.
Because it goes below 1.
Yeah.
Okay. Then, but when we see the shade cut, when we see the family like this,
it was not good enough.
it was not good enough.
Okay. Yeah.
There was a big
So
difference.
this is a very good example which we contest, because we would agree that this is still a difference, right?
Yes. Yeah, there is a difference.
Okay, then we make a test with this color. We measure which one is the standard.
Standard
This?
is wrong.
Okay. So we measure this as a standard. I do an average right now. This would be, by the way, the next recommendation I have to give. You should do always 3 times averaging on such samples because they show variance itself. And to show you what the effect is, we can set it to the statistics. Oops. And I measure just 1 time. Then I move the sample a little bit to just capture the whole area. And you see, this is quite stable. But if we would have a variance in this drawdown, or if it would not be fully opaque, maybe, we might have a bigger range here. But now, you see, in this case, we can forget about averaging because it's stable. Okay? So we call this, has this color a certain name? Once again? 08 B 17. I just call it standard right now. I do it into the test customer, and we go again here to give a certain tolerance. I would add here a delta E CMC tolerance. At CF is the delta E factor, the customer factor. So this is the delta E itself, and we keep it at 1. And I set this as a global default for the moment. I go back and say save and exit. So now we have this one color, and then we measure the other color against it. Without average, this is then the batch. I don't have to name it.
In trial, we cannot go average. Yeah?
Pardon?
Trial, experiment.
Yeah.
Can we go average?
Yeah, of course you can go average too. So this is here. And then I set it to 3, so we can do the same average like we did. Additionally to that, we can go to statistics here as well to see the range between the measurements. But now there was a problem at the moment. Once again. Here we go. There was a wrong measurement. So I reset and I start from the scratch. Then I move it again a little bit.
Automatically.
Yeah, it's for whatever reason it's flashing 3 times and then I don't know why.
No,
so here it's good. We move it a little bit. We measure a second time and the third time. You see, even this is stable. There's a problem with your computer, Heidi. Anyhow, I take these 2 averages and just save it to see the compare. Okay, this is now the point we get a delta E CMC of 0.66, and it is still a visual difference, you say. So this is exactly the point where we have to say, if this is not acceptable for you, we have to set the delta E CMC at a lower range.
What about the
or
DE star?
We take the DE star in such cases.
It will be higher.
It will be higher, yeah. It will be 8.6, but even below 1. So this is actually the problem we have.
Even delta E will be little more.
Yeah, a little more higher. It's 0.86, and the delta E CMC You mean this one?
Yeah.
No, this is 70. This is Hunter LED. This
Hunter.
is a totally different story. I would not use this at all. You take even the delta E.
Why this
Star?
value it is visually also closer?
In this case, yes, because the chroma is very low. So that means the rule for me would be I would not use a delta E CMC for chroma values lower than 20. Yeah. For chroma values lower than 20, I would use a delta E. And then in this case, we even would need to set a closer tolerance than 1. In this case, we would definitely have to set a closer tolerance than 1 because it's a visual distance.
What about that 2? That some factor 2/1.
Yeah, these are the factors to define how big the ellipsoid will be. So if we both agree that this is the problem, you can still stay with the delta E CMC, even with chroma values lower than 20, but adjust the tolerance visually, and this is the best recommendation I can give. I go back to database, say edit standard. This is our standard 08B17. I say edit. And I go into standard tolerances. And then I can go into modify. And in here I can say edit tolerance visually. And this is a very nice tool because what I can do in here is I can adjust. You see here is our sample, so the lightness is okay. But I can say this is still too less yellow or too bluish in a way. Yeah. So if I want to be this a fail, I could simply adjust the factor for chroma to a lower level, and you see how the ellipsoid is shrinking. And I could move it like this, that I would agree that this is a fail. If I do so, or I can leave this factor at 1, and I just shrink the whole delta E. So I define for this color, I have to be closer than 0.60 delta E to be, or maybe even closer than 0.50 to be safe. And then I say okay right now, and I say okay, and I save this one. Here I just can save it as an alternate description, which I don't do, and then immediately it becomes a fail because I set the tolerance different right now. So if I go back here to delta E CMC, you see it's still the same 0.66, but as I did shrink the ellipsoid, this is a fail color. And this is how you can adjust the tolerances step by step as you like it. So, and this is what I recommend anyhow. You should adjust the tolerance for each standard you are doing with known samples. Okay?
So is there anything default thing without adjusting? Because sometime I may go, the other person
The default would always be a 1 maybe, or you
default,
can
the formulation, default standard thing.
yeah.
If it is below 1, just do the thing. Yeah. Because sometimes we may keep some operators, not
No, of course.
Yeah.
Of course.
So what he has to do, just he measure it and he sees
No,
that
usually it should be one of you who measures in all the standards. So for example, if you want to measure all the RAL colors, someone should measure in all the RAL colors, and then you define a default. Then you define a default tolerance. And the default tolerance, for my opinion, would still be if I go to measure standard here. The default tolerance I have already set. I just measure something, it makes no difference at the moment. Average. Yeah. If I go to next, here I can set the default tolerances, and now I have defined a global default to be exactly a delta E CMC for spin with the lightness to chroma ratio 2:1, which is default, and the factor of 1 as the default value. But this default would now pass.
automatically it is going to 1. No? you released
Yeah.
the 0.6.
No, I did change it. I did change it. Automatically, whenever you create a new standard, it is going to 1, which is okay. We could agree on a 1.4.
What is that?
L is lightness. You see it here. You see, this is the borders for lightness, and if I set this to 1.4, it is shrinking, you see? So I could set this to 1.4 and maybe this to 0.70, but leave the delta E at 1, that it's easy for the operator. That in the end, if the value he gets is below 1, it's fine. Because if I shrink these factors, the delta E, of course, will increase. The value calculated will increase. So for our example, if I go back here, I just skip all this, and I go back into this standard by database edit standard, and say edit here, go into the tolerances, and now if I would apply this to this standard, so that means I keep the delta E value itself by 1, but I decrease the size of the shape to 70 and this one to 1.4 maybe. You will see that this 0.66 will change because we shrink the whole tolerance space. That means we shrink the factors for the calculation of this formula. I say okay, I say okay, I say okay. I don't save the alternative, I say just no, but you see immediately now we get a 0.93. So maybe in this case, as it still displays pass, we need to shrink it a little more.
But in the inside they have said not available to system. It's written there, no, in the inside that you give a helper.
Yeah.
The helper, no, it is not advisable to change that to DCMC like that.
Yeah.
DCMC tolerance, search, DCMC tolerance. The tolerance.
I cannot use the A because of the recording. I stopped the recording. So what we did so far, it will be okay.
Take that adjusting factor as one example. No?
Yeah, this is a very good example actually, because what we did is...
No, that's what we adjust for the close-up factor. This one keeps it safe.
Yes, it's already safe. It's already safe.
And we just we transfer there.
Yeah, now we can do transfer it back. So, what we did so far is we did check the color only for daylight. So if you say this is an interior use, we might have to check it for artificial light as well, which could be F11, which is a typical European standard. Or cool white fluorescent, which is F2, which is an American standard. And as we do not have a tolerance set for this condition right now, we still get a pass. And we see F2 showing 0.71, F11 not sure if it's now actualizing the data. No, it is. So D65 is 0.93 right now. And this is changing because the factors are default here again. We have a different look. I go again to database, edit standards, and I again edit this standard, and go into tolerances again, and then I add a tolerance delta ECMC again, but now for another illuminant observer condition, which is F11, 10 degrees. I keep it by 1, with the same ratios like we had on the 65, 1.4 and 0.17. I say okay. So this is exactly the same standard for another illuminant. And then I do the same for a typical light bulb, which is illuminant A, which would be a delta ECMC, illuminant A, 10 degrees. Always take the 10 degree observing condition. 1.4, 0.7, and the factor 1. So we have 3 times the same tolerance, but for 3 different light conditions. Very good. I say okay, I save it, and now we see immediately it fails. Because now we see, then we can check why it fails by observing the different light conditions. So we have set for F11, this is failing, and this is why we see the difference here. Because this is, F11 is according to the light we have here. This is fluorescent light. And fluorescent light is actually totally different than daylight. Okay? And then we could even check it for illuminant A. And here it's also very, so it's a borderline sample. It's a very good sample. I would, if you don't mind and can give me a cut, a piece of it, I would like to keep it because this is no, because what we see to check now the fail status, you get the fail here and you get the fail here. We can go into status, then the software tells us exactly what fails. And exactly here, this is the interior lens, F11, which fails. Very short only, but it fails. So this is a very good borderline example. Have you got any other example which you say, what about this? This color? So here we see as well a slightly bluish shade. Okay, let me make this. This is 04C33. By the way, if you flip the door down, you can always watch where you measure. So I would actually go and keep the set of these 3 tolerances default, because this is a good starting point anyhow. So if we go again to database, edit standards, and I just edit this one standard, or I go once again here in here to edit, even though I do not change anything, but I set this condition now as the default. Therefore, I can simply go cancel, go close here, and the next time I measure a standard, I will have this condition as default. Do you have any variance here with the spectrophotometer, USB? Okay. Oh. By dividing your computer makes me some trouble. We measure, hopefully, oh come on, it's the USB.